So today we gonna finish chapter 4, the entropy. So again, just recall the topics that we covered in this chapter. So this chapter we started with introduction to the second law of thermodynamics, and we said this law is important because the first law is not sufficient to describe the process can occur in a spontaneous way without any external force or will not occur. So this is why we have the second law of thermodynamics. And we said we have hundreds of statements describe the second law of thermodynamics, each one based on the experiments that these scientists did. And this statement reflects their observations. And in order to understand these statements, we discussed 4 concepts. We discussed what is meant by reservoir, what is meant by reversibility, the difference between reversible process, irreversible process, main features of reversible process, what is meant by heat engines, the work producing devices, and how can we calculate the thermal efficiency for heat engines. And we said we have 3 formulas that we can use to calculate thermal efficiency of heat engines. 3 of them can be used for irreversible process, and only one of them in terms of temperature of the hot reservoir and the cold reservoir. This one can be used for reversible process. Then we start to talk about entropy. So how entropy defined, where it came from. After defining the entropy, we define the universal statement of the second law of thermodynamics that combines all of the other statements, the different statements, in just one single statement that describe how can we describe the second law of thermodynamics and how it's related to entropy. And this statement says for any process to occur spontaneously without any external force, then the total entropy change should be positive. And according to this law, then we can understand that for the universe, the entropy is always increasing. Anything spontaneous is accompanied with an increase in the entropy. Then we mentioned some perspectives for the entropy, how entropy is related to spontaneous process or no, how entropy is related to the work loss. And the last thing, we explain the mathematical equation for the entropy balance, and we start having some examples on this. Today we have the last thing that we need to continue. This is related to entropy calculation. So we explained the entropy balance equation. We had 2 examples in previous lecture to see how we can calculate entropy. But today we will continue one of the special cases if we have ideal gas, and this ideal gas with constant heat capacity. So can we use certain equations to calculate entropy change or no? And the answer for this one comes from something called Gibbs relations. So we have relations, it's called the Gibbs relations. These Gibbs relations relate entropy to pressure, temperature, volume changes. Okay, so this is the main function of this Gibbs relations. It describes how the entropy will change with respect to temperature, with respect to pressure, with respect to volume. And then from these relations, we can mathematical equations that we can use to calculate entropy, again, for ideal gases with constant heat capacity. So this is the special case. So in any problem, if you have ideal gas with constant heat capacity, then the equation that we will present now, you can use directly to calculate the entropy change. So from where these Gibbs relations came from, so again, it starts from the first law of thermodynamics. First law of thermodynamics, we have the change in internal energy equal change of heat plus work. Change of internal energy, this is the total energy stored in the system. We neglect kinetic energy, we neglect potential energy with respect to internal energy. And here we have the dynamic forms of energy, heat and work. Again, for reversible process, we have ds is dq over t. So we can say dq is tds. So here in this equation, we can remove dq and we can put t ds. And again, from chapter 1, we know that the work is negative pdv. So also we can remove this work and we put negative pdv. So now we can rewrite the equation and say du, the change in the internal energy, is dq, which is tds, plus dw, which is minus pdv. If we rewrite the equation, put TDS on the left side, so we have TDS is du plus PdV. Okay, so this is one of the equations we have. Again, if we recall chapter 2, we have relation, like relates entropy with enthalpy. We know that enthalpy is internal energy plus PV, then we can say internal energy is enthalpy minus PV. Then we can put in the equation. Here in the equation we have du, and here in the equation we have u. So what is the change we have in the internal energy? So du, this one will be dH minus PV. Okay, because internal energy is everything here, is H minus PV. Now we need to distribute the derivative. So dH, this will be half, minus dPV, and this what we have here. And do you remember the derivative of two properties or two variables? It will be the first variable times derivative of the second one, plus second variable times derivative of the first one. So if you have dxy, this is from calculus, derivative of two variables multiplied together. So this will be the first variable times derivative of the second one, plus second variable times derivative of the first one. So this is why here minus PdV, this term, we have it in this way. First variable times derivative of the second one. Second variable times derivative of the first one. So all of this is equivalent to du. So now substitute everything here in this equation. So we can say TdS, this one is du, which is dH minus PdV minus VdP, plus the last term, PdV. So if we put all of these equations here, this will be a new equation to calculate TdS. You can see that here we have minus PdV, here we have positive PdV, so this will be cancelled. So we have TdS is dH equal minus VdP. So we have two equations. These two equations can be used to calculate the change in the entropy, one in terms of internal energy, another one in terms of enthalpy. These equations come from the first law of thermodynamics and the relation between the thermodynamic properties that we explained in chapter 1 and chapter 2. These two equations here, these are called Gibbs relations. And these equations describe, or they came from the first law of thermodynamics, with again enthalpy definition, internal energy definition, and it describes how the entropy will change with respect to different measurable variables, with respect to pressure, with respect to volume, with respect to temperature. So far is clear? Okay, so we have these two equations are called the Gibbs relations. We will use them again in chapter 6, these Gibbs relations. Okay, but this is an idea about where these Gibbs relations came from. Just relating entropy to pressure, temperature, volume, internal energy, or enthalpy. So now we have these two equations, Gibbs relations we have. These properties, all the properties we have in Gibbs relations right now are extensive property, depending on the size of your system, right? And this is something we don't prefer in the analysis. We prefer to work with intensive property, that size will not change the value of property. So we can divide all the equations by mass or divide all the equations by mode. So if we did this, then we can have Gibbs relations in terms of specific properties or molar properties. Here also specific properties, molar properties. If you remember from previous chapter, we said when you see this hat, so this means you have the property divided by mass. When you see this V molar, so this means we have number of moles, volume divided by number of moles. Okay, so this underline or this hat describe if this is specific or molar. Now, if we recall that, again, we need to have an equation for ideal gas. For ideal gas, we know that PV equal in RT, the ideal gas equation of a state. If we rewrite this equation, we can see molar volume is RT over P. Just rewrite the equation. And again, for ideal gas, and if you need to calculate the change in the internal energy at CV dt, change of enthalpy as Cp dt. Okay. If you put all of these observations, all of these equations in the intensive formulas we have here, then you can say TdS equal, instead of du, we will have Cv dt if you have ideal gas. PdV, again, pressure is RT over V. So we have this equation. Divide everything by temperature to have the entropy on the left side. So the entropy will be Cv dt over T plus Rv over dV. The temperature will be cancelled. If you integrate this equation, you will end up with this equation here. An equation you can use to calculate the change in the entropy. Again, if you have ideal gas with constant heat capacity, these two conditions should be applied. If you don't have ideal gas, you can't use this equation. If the heat capacity is not constant, you can't use this equation. So this equation, an equation derived from Gibbs relations, you can use it to calculate the entropy change for your system if your system is ideal gas and the heat capacity of the system is constant. Clear? Ezra? Clear? Okay. We have same thing we can do for the other side. So we have dH. We can say it's Cp dt. Specific volume is RT over P. Divide by T to have only ds on the left side. So we have Cp dt over T minus R over P dP. Again, by integration, then you will have this equation. ds is Cp ln T2 over T1 minus R ln P2 over P1, or plus R P1 over P2. Again, here we have plus, here we have minus, because here we have P2 over P1. Here just we flipped it, P1 over P2. So the same thing. So again, all of these equations, you can use any one of them to calculate entropy change based on the given you have. So if you have like temperature, smaller volume, CV is given, you can use this one. If you have CP is given, you have information, given information about the pressure changes, temperature changes, then you can use this one. These two equations will give you the same result. So based on what given information you have in the problem, you can select any one of them to calculate the entropy change. And again, the key here, you can use any one of them if you have ideal gas with constant heat capacity. Clear? Any questions? Okay. This is just a repetition of the equations here, and the most important thing is this last part. So again, here you have R exist in the equations. So based on the units of R, then you have CV or CP units also should match. So if you have R, for example, joule per mole Kelvin, then the heat capacity value should be per mole. If you have R, the ideal gas constant per kilogram, then CV should be per kilogram. R per kilomole, then CV should be kilomole. So the units of CV are, and this are even CP and R in this equation, should be consistent. All of them per unit mole, or all of them per unit mass. So again, consistency of the units is very important in this one.